You don't really need to know all the details of a mass spectrometer. Like, he's going to talk about all the pieces. I just want you to understand the basics of how it works, because our main thing is the interpretation of the graphs that come out. Okay, here we go. No, that's not a video.
We begin with the simple.
Okay. Now he's going to start with an analogy that I really like, that we'll kind of refer to a lot. You'll tell from his accent that he's obviously not from the U.S. I think it's Irish. I don't know my accents very well, so correct me if I'm wrong. But he's somewhere European. So just to clarify, does anyone know what a snooker ball is? I didn't know either.
Snooker ball.
Anyone know what a snooker ball is?
Is it bigger?
I guess that's wherever he's from, that's what they call a pool ball. Or like a billiard ball. So as he's referring to this, that's what a snooker ball is. A snooker. Okay.
Analogy to get across the most basic principle of the mass spectrometer. 3 balls of equal size but different mass. The lightest ping pong ball, straight down and straight through. Somewhat heavier, golf ball, straight down and straight through. And the heaviest, the snooker ball, straight down and straight through. The hairdryer would be put on at this point, blowing air from right to left. Look at the deflection of each ball. 5 for the lightest, the table tennis ball, 3 for the golf ball. And what about the heaviest? Snooker ball has the least deflection, score of just 1. Conclusion then is the ball with the greatest mass is deflected the least.
Okay, stop there for a second. So this analogy is the basics of how a mass spectrometer works. Okay, is you can take a sample of an element, let's say carbon again.
That makes sense.
Okay, they pour it, they vaporize it, it actually has to be in a gas form, but they put the carbon into the mass spectrometer, and the mass spectrometer can separate the sample based on the different weights of the isotopes. So it's pretty much the same idea, right? How the balls get deflected depending on their mass, right? The ping pong ball got deflected more than the snooker ball did, right? Anyone in here a fan of NCIS? Anyone watched that before? Yeah, everyone knows, but it's like a crime scene show. Other crime scene shows actually talk about it, but NCIS is the one I've heard it the most, where the lab tech Abby often refers to her mass spec machine. Because mass specs do a really good job at identifying unknown substances. Where, once again, at a crime scene is very plausible, right? You get there and there's a white powder. You're not just going to take a lick of it and see what it is, right? You shouldn't. Maybe you guys would, but that's why you're not further scientists yet. Okay, but they can literally take that sample, put it into a mass spec, and from the data you get, you can identify what the sample is. In our case, we're focused primarily just on the isotopes of them. Now, with isotopes, all isotopes are not created equally. Okay, if I have a sample of carbon, it's not 33% 12, 33% 13, and 33% 14. It's actually majority of carbon is carbon 12. The other ones exist, but most of it is carbon 12 in the universe. And so when we calculate the average, it's known as a weighted average. It's not a true average. Because if I took 12, 13, and 14 and took a true average, what would I get?
13.
Right in the middle, 13, right? But for carbon, look at where it lies. Its average is 12, which means there's way more carbon 12 in the universe than there is of the other samples. Yeah, Kimberly.
Why do they have different numbers of
Neutrons?
Like, why does that happen?
I don't know if there's an answer for that. That's a great question. I think it just, yeah, they're just there. I don't know if we know why it's there, but for whatever reason, some of them are created with more than others. That's my best answer I can think of, but I'll let you know. Yeah, I don't know if we know. That's one of the hard things with chemistry is there's so much we know, but then there's other things that we are understanding the patterns and things. When you get down to the root of like, well, why? Like, well, we don't know yet. We just know it does this. But yeah, good question. So, okay. We're now going to watch just a little bit more. It's going to show you an actual mass spec once again in his drawing form a picture. And then we'll get into dissecting the breakdown of it.
In the mass spectrometer, a magnet plays the role of the blow dryer. Look at the labels: a heater element to create a vapor, an ion accelerating field which gets the positive ions streaming from left to right towards the magnetic field, a detection plate at the top right there. The entire mass spectrometer is enclosed and is evacuated. There are no air particles inside, so that the beam of ions has a free run. No air particles to strike. In the copper color, you see two rectangles. One at the bottom is the electron gun. It's an element which is heated and generates electrons, which are attracted towards the capture plate, the larger of the copper-colored rectangles. This produces a beam of fast-moving electrons. Entering at the bottom left there, you see the sample represented with green spheres. If it's not already a vapor, your sample would have to be heated to create a vapor. We'll have our sample might be ions, atoms, or molecules. If it is atoms or molecules, we have to change the atoms or molecules into ions. This is the role of the electron gun. The electrons will knock off one or more electrons from the atom or molecule. When an atom or molecule loses an electron, it doesn't affect its mass, as electrons have negligible mass, but it will create a particle which is a positive charge, or too positive if it loses two electrons.
Okay, so once again, basic idea, once again, you're not ever gonna have to like draw a picture of one of these or really describe it, but in understanding how it works, it helps us better understand our graphs, okay? So the sample comes in here, it gets vaporized, turned into a gas. The electron gun is what gives it a charge, because it's not a blow dryer, it's a magnet. And in order for a magnet to affect something, that thing has to have a charge on it, right? Otherwise, if it's neutral, it wouldn't be affected. And then it goes through the magnet, it gets deflected depending on its mass, and then it hits the detection plate, which then we get these bar graphs from, which is what we're going to look at now. Okay, all right, so you can go ahead and flip over to your notes. Where'd it go? The notes used to be behind there. Pull it up again, I guess. Okay. Mass spectrometry is an analytical technique that utilizes the degree of deflection of charged particles by a magnetic field to find the relative masses. So once again, the main objective here that we're looking at is this idea of differing masses. In our list of 4 things of what a mass spec can do, if you want to put stars next to these 2, that's how we're going to be analyzing our graphs. This one is, like I said, that's like what you can do with a mass spec. If you go on and take organic chemistry, you'll learn how to interpret those graphs of mass spec, but for us, we're focused on single isotope graphs, not a combination of things, okay? All right, let's go through once again, just to get it, the steps of how it works. Okay, so step 1 is it's going to be ionized, meaning we have to have a charge on our sample. So that's where it's bombarded with the electron gun to give it a charge. Okay, once again, so that it can be affected by the magnet. Okay, and then those fragments, I guess if it was a molecule, so like in terms of an unknown, right, then the molecule gets broken up into lots of little pieces. But for us, it's just the atom, so the atom just gets separated apart from the other isotopes. Okay, step 2, there's a pair of oppositely charged plates in the ion chamber, and the positively plate charges cause it to be accelerated as it heads through the tube. So they put some speed on it. Okay, step 3, the analyzer tube is then surrounded by the magnetic field, which changes the pathway. So that magnetic field shifts it one way or the other. Yeah.
So I was just wondering with the magnet,
Yeah.
is it like pushing, like is the magnet negatively charged or positively charged?
I'll double check this. I'm pretty sure it's positively charged.
So it's pulling.
Well, so like in this picture, because it has both, like in the field. So the side that it's influenced by would actually be the negative side, though, I'm pretty sure, because that's why the lighter ones get pushed farther than the heavier ones. So good question, Taylor. I'll double check that, though. The magnet, right? So that's like our blow dryer, sends it through, pushes it to a side, and then finally the part that we're going to focus on is the spectrum. Okay, what we get in the end from the data. Okay, so a spectrum is created which tells us these different things in terms of how often something hit in a certain spot, and it can then be calculated of its atomic mass as well. The nice thing is we don't have to do the equipment itself, the mass spec gets all that for us. We just get the graph, and now we're going to learn how to interpret these graphs. Any other questions just in general about a mass spectrometer? Yeah?
How big are they?
They're not very big. I mean, I haven't worked on one personally since college, so it's been 8 years, so maybe they're even smaller now. But the one at SUU, and it was an older one too, so it's not like the most high-tech ones. It was like a box like this. Because all that's like inside of it, right? You can't see it. Because as they mentioned, they have to vacuum out all particles, so it's empty space. So yeah, they're not very big, and they just put tiny little, because you don't need tons of a sample, right? Because in a small amount of a lot of atoms. So yeah, hopefully if you do, once again, yeah, if you choose to study chemistry, you'll get to work on one in college and stuff. So when COVID is taken care of, I would love to at the end of the year to have you guys go do a tour at one of the universities. They always offer to like go walk through their labs and see all their super cool equipment that they have. So, okay, any other questions on that? Okay, this right here is a lovely mass spectrum. Okay, pretty much they're very simple. They look like a little bar graph with a bunch of different lines. The number one thing whenever you're looking at a mass spec that you want to look at first is the base peak. The most valuable information to you, the base peak is the tallest one. What that tells you is that that is the most abundant isotope there is. Meaning that its average is going to be the closest to that peak. Okay? So once again, the first thing when you're looking at one of these is what is the base peak? Now at times, you may find, so most of our peaks are in this range, right? And then there's like these random ones over here. If we're analyzing if this was a mass spec for a single element, any guesses of what random peaks far away from the rest would mean?
Different elements?
Yeah, it wasn't a pure sample, right? Because it wouldn't make any sense that it's not with the rest of the average. Okay, but be aware of that because they love to throw new things at you if you saw that. But that's what it would mean is, yeah, you had something else in your sample that wasn't just carbon or whatever it is. So, okay, let's look at one for copper. So this is another one, a little simpler, but same idea, mass spec for carbon. Okay, what it tells us is it tells us a few things. Number one, the number of peaks correspond to how many isotopes there are. So each peak is a new isotope. So if a question said, how many isotopes does something have? You would count how many peaks there are, okay? Second thing is it tells you which isotope is in the greatest abundance and by how much. In this case, we have copper 63 and copper 65 are two isotopes. Copper 63 makes up 69% of all copper in the universe, and then 31% is copper 65. Which, if you look at the periodic table, matches that the average is 63.5. Once again, the average gets pulled towards the greater abundance. And this is the equation that is used. So the way that they mathematically, once they get this data, the way they mathematically calculate the atomic mass, and this is actually very similar to how like a weighted grade is calculated, right? So like in a class where it's not equal point distribution, it's the same equation. Okay, but the way you calculate a weighted average is you're going to take the mass of the isotope, okay, and multiply it by its percent abundance. Okay, so you take the isotope's mass times by the percent abundance, plus the next isotope's mass times its percent abundance. And then you would continue that for however many isotopes the sample has. Now, keep in mind that mathematically, when you do percentages mathematically, you always have to change them into decimal form. So if I was going to solve this problem for copper, I would say, okay, well, the isotope's mass, so the first one is copper 63, so 63 is its mass, times by 0.69. That's its percent abundance is 69%. And then plus copper 65 times 0.31. Questions on that equation? Yeah, Carly.
So that tells us the atomic mass of the substance we put in there?
Yes. Yeah. So obviously, rarely is a question going to say, hey, here's a thing for copper, what's its atomic mass? Because what could you do? Just look at the periodic table, right? Like, we really don't need to calculate it. Most likely it will be they don't tell you what the sample is, and then from this answer, you can figure out the element. Or we'll look at another way that they kind of flip it as well. But great question. Any other questions? Okay, so we're going to do a practice problem here. This is more just another skill thing, because once again, we already kind of know what the answer should be, but just to make sure we understand how to use this equation. They didn't get printed on your paper like I thought they did. So you could like squeeze the practice problem in either like at the top or at the bottom, wherever you want to throw this in. But with your table buddy, practice the equation for this problem. Okay, so here's our magnesium data for our isotopes. Check yourself that you know how to use the equation, and you should get 24.31 as your answer. If you don't, then you're doing something wrong. Yeah. Is that better? I want to like talk to someone and see if I can get a whiteboard that goes all the way to the ceiling, and then I'm gonna get one of those ladders like that like libraries, and then I could write really high up there.
So we're like supposed to find like that. So I think we just unfortunately
Yeah. Ask. Yeah. Oh, I gotta answer the sig fig questions that people asked. I wrote those down. I forgot. Oh yeah. Anyone else want to borrow a calculator? Once again, I just want you to practice the setup of the equation before we take it a next step up. Once you're done, set your pencil and calculator on your paper. You know you're finished. again, you should get 24.31. If you get that, then you did it right. Alright, I'm seeing most calculators down. Any questions before we twist the problem a little bit? Yeah, why did they because of the percent abundance. Because that is like a measured value. Because, so in this case, so you are timesing, right?
Right, but since we treat it like a decimal, right?
So since the percentages went to the 100th place,
Okay, so
our
that's-
answer could go to the
Okay, not what we used to multiply when we moved the decimal, so we forward.
Yes,
Okay.
yes. Yeah, because you still would go back to like the original. Oh, I see, because we changed it to a decimal to use in the math. Oh, yeah, that wasn't a bad thought, though. But yeah, because I think it's just because you're going back to the original, the way it is. But yeah,
It's like, I'll never understand something, so that's.
yeah, yeah, go ahead. Okay, any questions on this one? Okay, before I forget, let me address just a few. Most of you said you were good with sig figs when I looked over the questions, but a few people had some good questions that I just want to address, and then we'll go on to the next problem here. So, exact versus inexact numbers, and the majority of the numbers we work with are not exact because we're measuring them, someone else measured them, the equipment's not perfect, so on and so forth. The only things that are exact are things you count, because I can count with 100% certainty how many students are in this room, and it's not an estimate, right? And then any conversion factor, because saying that there are 12 inches in a foot isn't like an estimate. Like, no, we know that there are 12 inches in a foot. And so when something is exact, you don't think about it for sig figs. You only focus on the inexact ones. What was this question? Oh, if by chance we were adding two numbers that didn't have decimals, you'd still go to what's considered like the place location. So like, if I was adding 22 and 101 for sig figs reasons, right? So mathematically I'd get what? 123? This one goes up to the tens place, so that's where I'd actually round my answer to. So significant figure-wise, your answer would be 120. Because that 3 we can't keep, so it just becomes a placeholder. That's pretty rare, I'll be honest, because these are very inaccurate measurements to not have decimals. So I would say like pretty much everything we use will have a decimal, but yeah, Isaac.
What if one of them has a decimal though? Like if it was 22 plus 101.3 or something like that.
So you always go to the least accurate one. So that wouldn't actually still matter because the least accurate. So, does that make sense? Kinda?
Yeah.
Okay. And we'll keep, I mean, obviously sig figs are something we're going to be doing all year. So if you're still a little uneasy about them, they will come. Okay. Next problem I'm going to show you. Here's what I want you to do. I guess let me pull up the problem and then I'll tell you. Okay. Oh, pull it out a little bit more. So this question says that the average atomic mass of naturally occurring neon is 20.18. There are 2 common isotopes for it. Use the information in the table to calculate the percent abundance. So we're kind of using the same equation a little differently. So I'm going to give you 4 minutes to try this as best you can on your own before I just show you how to do it. Because I want to start training those brains to problem solve. Okay, so you talk to your table buddy about it. Get some ideas, write it out. How would I solve this problem? Go.
So before we knew that, it was
We don't have the
different.
Once again, in AP, I'd rather have you write something, even if you're not sure it's right, than to do nothing at all.
But this specific number, we could just plug in numbers. So we know it's closer to this way, so we know it's more than this one for sure. So this calculates formula. We know the atomic mass. I won't say atomic mass. So you just divide the atomic mass by the percent. Right? Does that make sense? I'm not sure.
See some confused looks on our faces, and that's a good thing. That means our brains are having to think.
Yeah, so you see them separate.
Find somewhere to get rid of them. Exactly. Yeah, no.
That's it.
This is pretty close.
Yeah, answers looks like 90%
Oh, I got it.
and then only 10% for
And then we subtract.
21. But we could go into keep guessing. That would take forever. And so
Okay, raise your left hand if you want to keep going, because you have an idea. Raise your right hand if you surrender. Meaning, I've gone to a point, but I kind of am stuck. Both, maybe a little, that's true, you could raise both. I just want to know, before I start going, does anyone want to keep working a little bit on their own? Okay, I'll give you a few more minutes and then we'll go
I
over
want to
together.
try the 10 spot, see like how close we can get to the real answer.
It's some random math and you can try it out on top. My brother
Oh, that's
and the kid divided and then just like something like that. He's like for no reason, he got the answer to that. It's like you can get it right, right? Wait, man, what are you thinking?
Okay. Well, okay, if you want to keep going on your own, that's fine. I'm just going to start giving some hints for those that are stuck. Okay? All right, anyone tell me where they started. What do we know? Any ideas? Yeah, Erin.
So we have that formula that was written before,
Yeah.
and then you just plug in numbers, and you can get the percent.
So she's saying, so we'll take the same formula, plug in what we know, right? So we know this time the final answer, right? And then we know the mass is 19.99, but we don't know the isotope, right? So I'm just going to put X, okay? I mean, we don't know the percent. Plus, we know the other mass Like so. How many of you have an equation like that on your paper? Have a smiley face if you got that equation, because that's a great starting point.
What if you did an X instead of a Y?
That's fine. Wait, 2 X's?
Yeah, I did 2 X's.
Ooh, you used to have a smiley face, but there is a problem. They could be.
But it doesn't because it doesn't average together.
Okay, so then there's something else we also know. So how do I know they're not the same, Evan?
Because you could just average those together, it's like probably like 20.4.
Yeah, we know because if this is the average, which one is in greater abundance?
19.
This one, right? Because this is way close. This is closer to the average than that one is, right? So we also know that x has to be greater than y, which is a great conclusion to draw because if this was a multiple choice question, you might just be able to pick your answer from that knowledge, right? You wouldn't have to actually solve it. Now, what I heard from a lot of people and kind of what Aaron says is you could then just keep trying numbers until it works, right? You could, but that would take longer than you probably want to spend. Anyone else have another idea about what we can do next? Kimberly.
Okay, so this also takes forever.
Okay.
So if you want to get it in terms of one variable, right? So you could say like subtract 21.99y from this side. It's easier if I just show you, but so we get basically down to where we just have x is equal to whatever's on the other side, and then we plug all of that in for x. So we're only dealing with y variables. Takes a while. But
So she's bringing up though the main dilemma here, right?
Yeah.
The main dilemma, and this is like
it's two variables.
true mathematically and no matter what. If you have 2 different variables, it is impossible to solve the equation without a second equation. If you have 2 variables, you have to have 2 equations. Just like if we had 3 variables, you have to have 3 equations. So what's another equation about x and y that we know?
X plus y equals 1.
Why?
Oh, that's good.
Their probability.
Oh.
Because these are percentages, and in decimal form, well, that was like, I just saw light bulbs pop all over the place. Okay, so when you're solving problems and you get an equation, if you have more than one variable, you got to start thinking, okay, what else can I do to get a second equation? Now we can substitution, right? Going back to algebra. Okay, so I'm going to do x equals 1 minus y.
Yes, and then put that in.
And then take this, put it in there. Now I only have one variable to solve for. Questions on where that all came from? Okay, so problem solving skill here, right? In the future, if you start writing equations out, which is good, for every variable you throw into your equation, you've got to have another equation for it. Yeah?
Will x plus y always equal 1?
In this case, yes, because they're percentages, right? And percentages are always going to add up to 100%, which is going to be 1. So, good question. Any other questions before we just go through the algebra side? Now, sometimes when we do just the math side, so once we get past the chemistry setup, which we've pretty much done, now it's just math. If you ever need more help with the math side, don't hesitate to let me know. Sometimes I'll just go through it fast because I'll just assume we know how to do it. But if you need help mathematically with a skill we're doing, don't hesitate to stop. So, once again, as I'm going, stop me if I lose you. Okay, so we're going to substitute this into here. So I'm going to have 20.18 equals 19.99 times 1 minus y. 21.99 plus, or times y. Okay, so I just substituted it in. Now I'm just going to start simplifying things down because we just want to get y by itself. So the first thing I would do is I'm going to distribute that to get rid of that parenthesis. So now here's my distribution step. So we're going to have 19.99 minus 19.99y plus 21.99y. Technically, I don't need this parenthesis anymore. Okay, so I distributed. Now I'm going to combine like terms. So I'm going to combine my two y's and move this to the other side. Okay, so I'm minusing this to the other side. And then I'm going to combine those two together. So we get, what, 0.19?
Yep.
And what am I doing? I'm combining these two, so 2y. Stop me if I lost you. Now I'm going to divide by 2. So y is going to equal 0.095, which in terms of an answer, you would report it as 9.5%. And then x is 1 minus that, or the percent minus 100. So then x would be, what, 90.5? Questions on that? Okay, and just kind of like to show you like comparison once again of like skills versus the way we're going to see it on AP. This is like an AP style type question. The skill is knowing the equation, but rarely are you going to just use the equation as is. Right? They like to twist things up. So, any questions on that before we look at one more problem together? Yeah, we got okay. Okay, I just want to show you an example of a multiple choice question. Okay, I'm going to put this question up on the board. What I'd like you to do, though, is keep it quiet and just answer this one in your head so everyone can kind of answer for themselves, and then we'll make sure we're all on the same page. This is one from today's quiz, yes. Okay, so the question says, which of the following elements has the mass spectrum as shown? Sorry, it's not super screen friendly here, so so there's your spectrum, and then those are your options. Okay, so once you've come to a conclusion, just keep it in your head.
Can you show us the graph one more time?
Yeah.
You scroll up one more time.
Uh-huh. There's your graph. CF, I think, California.
Did you pass?
Okay. Everyone have an answer? Okay, here's what you're going to do. You're going to pick up your periodic table. Okay? And on the back of it are the letters A, B, C, D. You're going to hold it to show me what your answer is. Does that make sense? Thank you. I tried. Teacher big brain moment right there.
Exactly.
Okay, but no spinning it. So people just like tossing them. Okay, oh, I'm seeing some good letters. Seeing some okay letters. Is that turned around? I can see it. Oh, you're pointing to it. Sorry. Okay.
It's like those just throw away.
Okay. Put your things down. The correct answer is B. Okay, so let's make sure we understand the why. Okay, so what did we say? What's the first thing you should look at with a mass spec? The base peak. Right? This is how I would solve it. Is I'd go to the base peak and I see, okay, the base peak is 98, which means the atomic mass should be close to 98. So I'm going to go to the periodic table and just find something that's close to 98. TC, but that's not an option. The next closest one is MO, which is an option, and that's the answer. You could also go and check all four, but once again, think of we want to solve these problems as fast as we can, and to check every single one takes time. So it's faster to find the mass to the element than not. Questions on that? Okay, this is one of your questions on your quiz tonight, so don't miss it again if you missed it right now. So, okay, homework assignment, there's a mass spec Canvas assignment, so just some more questions like this. Classroom quiz, and you have to read one page. Page 52. Okay? It's not even the whole page either, it's just like a little box about mass spec, so it's just the only thing in your entire book about it, which is a little weird. Yep, see you, Claire.